Today we're looking at a very important and very powerful reaction in organic chemistry called the Diels-Alder reaction. The Diels-Alder reaction does one thing and one thing only. It's very good at what it does though. And that is it makes six-membered rings. It makes cyclohexane looking things. And so whenever you have a synthesis problem where one of your, it seems like a six-membered ring was formed, well then the Diels-Alder reaction is probably going to be involved. Let me show you how the Diels-Alder reaction works. And I'm going to tell you right now, this reaction is different than a lot of the reactions we've seen in this class, in that we don't have a traditional nucleophile and electrophile. Let's take a look at what happens in the Diels-Alder reaction. It starts with an alkene that looks like this. This is a conjugated 1,3-diene. Okay, let's break it down. Conjugated because it's got two double bonds that are separated by a single bond. Remember that alternating double bonds we call conjugated. And it's a 1,3-diene because there's two alkenes. Ene means alkene. There's an alkene starting at the 1 position and another alkene starting at the 3 position. So that is why it's called a conjugated 1,3-diene. You're probably thinking this is a pretty unusual starting material for a reaction, and sure enough it is. We've seen, a lot of reactions start with alcohols and leaving groups, bromines, alkenes, but we haven't actually seen a reaction where it requires two alkenes, and not just any two alkenes. They have to be specifically conjugated, and they have to be on atoms 1 and 3. So that is very specific. Now, what is this conjugated 1,3-diene going to react with? It's going to react with something called a dienophile, which is really just an alkene, another alkene. So this is called the dienophile because it loves the dienophile. It loves the diene. The ending phile means love. So diene lover, and it's just an alkene. So we've got a diene and a dienophile. Now what the heck are these things going to do with each other? They are going to do the Diels-Alder reaction. And I should just mention the dienophile is simply an alkene, or we'll see example of it as an alkyne as well. Okay, so let's see what the reaction actually does. So here's an example of the reaction. And so if we take the simplest diene, which is butadiene, it's just got carbon and hydrogen on it, and we add to it ethylene, which is the simplest dienophile, it will form a six-membered ring with a double bond on the left. And if you notice what's actually happened here is it's creating two new sigma bonds. It's basically the ends of the molecule are becoming connected together so that we have two carbon-carbon bonds forming. And I've highlighted those two new bonds in yellow. Let's take a look at the mechanism of this bizarre reaction. The mechanism belongs to a class of mechanisms called pericyclic reactions, where there's a movement of electrons in a circle. Let's take a look. So we have our diene, and we add our alkene dienophile. And what's going to happen is, I want you to imagine kind of drawing a dotted line connecting the ends of the diene and the dienophile. You can almost see the six-membered ring is starting to form. Now, you don't need to draw the dotted line in the reaction, but I'm going to leave it here in the mechanism to help you. The arrows are going to be as follows. The dienophile acts first and puts electrons in the space between. There's no bond right there, but it's adding electrons to the space in between where the dotted line is. A second arrow occurs from the diene to the middle carbon of the diene, and then a third arrow from the diene to that sort of nether space in between the diene and the dienophile. So you can see it looks kind of like the recycling symbol. There's like these arrows going in a circle. So arrow 1, arrow 2, arrow 3. And it doesn't matter if your arrows go around to the right or go around to the left. It really doesn't matter. Just pay close attention to those arrows. And notice what's happening here. This arrow right here is what creates a new double bond by doubling down on this single bond, making it a new double bond. So let's take a look at the product. There we go. We've got our two new sigma bonds here. and we've got a new double bond in the middle there. Now, an important note of this reaction is that the diene has to look like a C. It has to be in the S-cis conformation, as we call it. In other words, it has to be able to bend so that it can point towards the dienophile. That's important for this reaction. So for example, this is the S-trans diene. Looks like an S, kind of. So this is S-trans. And this isn't going to work for Diels-Alder, okay? But S-cis will work. And you can see it's the same molecule, just rotated around the central single bond. It's going to be important that the molecule can get inside of the S-cis conformation for the reaction to work. Now, the only time that a diene would not be able to rotate into the S-cis conformation, it's a very rare situation. It's when you have something that looks kind of like this. See, this is a 1,3 conjugated diene. It's got everything you think you'd need from the diene. It's conjugated, it's got alkenes one apart, but notice how the ring locks it in the S-trans conformation. You can't rotate around this single bond because the rest of the molecule is in a ring, so it won't take that with it. So for that reason, molecules like this are unable to participate in the Diels-Alder reaction because by virtue of the fact that they're in a ring, they are locked in the S-trans conformation rather than S-cis. That doesn't mean you can't have an S-cis alkene in a ring. In fact, it's very common. For example, you can have the other situation too. Here's an alkene that's locked in the S-cis conformation. So just because you're in a ring doesn't mean you are prohibited from doing the Diels-Alder reaction. Just look and make sure that your alkene is in the right conformation, which is S-cis. And to make it easy for you on the exam, I will put the alkene in the S-cis conformation for you, so you don't have to worry about rotating into different conformations. Just a side note. Now, it turns out that this is the simplest case Diels-Alder reaction, but it doesn't actually work very well. And there's a number of things that we can do to make this reaction better. So Diels-Alder reaction it works best when we add certain groups to each piece. So it works best when the diene is electron rich. So we can make the diene electron rich by adding electron donating groups to it. And electron donating groups, we're going to talk about it a lot, so let's just abbreviate it EDGs for short. And what is an electron donating group? We'll talk about that in a moment. It also works really well when the dienophile has electron withdrawing groups. And we call those EWGs for short, so we don't have to write that whole thing out again. So for example, if we had this diene, it kind of sucks for Diels-Alder reaction because it doesn't have electron donating groups on it. But if we add to it, say an electron donating group down here connected to the diene, or you could connect it to one of the central atoms, any one of the atoms actually. I'll just create a little bit more room here. EDG. Either one of those is much better than just with nothing. So adding the electron donating groups makes it faster. And then that would be paired with a dienophile with an electron withdrawing group. This would be the best case scenario, where you have electron donating group on the diene and electron withdrawing group on the dienophile. All right, so the next order of business is we have to actually define what are electron donating and electron withdrawing groups. So electron donating groups and electron withdrawing groups involve resonance. Which is the most important factor. and also induction, which is a less important factor. Okay. Let's take a look at an example of an electron donating and electron withdrawing group. So one example of an electron withdrawing group, a very popular one, is an aldehyde. So if we have a dienophile, which is just an alkene, and we connect to it an aldehyde, let's draw a resonance structure to show why the aldehyde is electron withdrawing. We can draw a resonance structure, which is pi next to pi, kick electrons up onto oxygen, and what you can see here is that it leaves a positive charge on the dienophile. So aldehyde pulls electrons from the alkene via resonance. We know it pulls electrons away because we're left with a positive charge on that carbon. Thus, aldehyde is an electron withdrawing group. So aldehydes are great to put on dienophiles. They're terrible to put on dienes. Let's take a look at an electron donating group, and then I'll just make a list for you. So let's consider an ether. Okay. So when you have an ether, we can draw a resonance structure that actually pushes the other way. So the arrows go down towards the bottom of the alkene. This is lone pair next to pi. If we draw this resonance structure, we'll see puts actually a lone pair on the alkene. So the oxygen donates electrons via resonance. So it's electron donating group. So you would not want to put an ether on a dienophile because it donates electrons to the dienophile. You want to put withdrawing groups like aldehydes on dienophiles. Now, the clever students out there will notice that oxygen is actually electronegative element. It's delta negative, and carbon is delta plus. So inductively, oxygen will steal electron away from the diene. So inductively, oxygen is withdrawing. So what you'll notice is there's sort of two competing factors here. Resonance for the ether is donating because it's kicking electrons towards the alkene. Notice that we could not draw the arrows going the other way. A very common student error is to think that the arrows could go this way, away from the alkene towards oxygen. But remember, we can't do that. Okay, that's not a valid resonance structure. You can't move electrons towards lone pairs. That would be putting 10 electrons on oxygen. So don't do that. So we can see a resonance structure that pushes electrons away from oxygen onto the alkene. That's donating. But then we see an inductive effect that sucks electron density away from the alkene. So who wins? Well, just like we said above, resonance is most important and induction is less important. So even though we have two competing factors, an ether is still considered an electron donating group. Let me just give you a list now of some good electron withdrawing groups, and then on the next page I'll give you some good donating groups. So good. And see if you can notice a pattern with all of my electron withdrawing groups, or most of them. Okay. So the most popular category of electron withdrawing group is the carbonyl. So if you have the following substituents connected to an alkene, it is withdrawing. So an aldehyde, the little squiggly line shows where it's connected to the rest of the molecule. You could have a ketone. You could have an ester. These are withdrawing carbonyl groups. In other words, C double bond O. That's a withdrawing group. Another one is nitrile. That's when you have a CN triple bond connected to your alkene. That is a strong withdrawing group. So this is going to be the CN pi bond. Those are withdrawing. Nitro group Nitro group we have not seen before. Nitro group is NO2 group. It looks like this. And this is the NO pi bond. All right, and one more electron withdrawing group that I'll give you here is the trifluoromethyl group. Trifluoromethyl is just CF3. And this is just an inductive withdrawer. No resonance. It's just a strong inductive withdrawer. So I want you to notice that except for the trifluoromethyl electron withdrawing group, all the other electron withdrawing groups have something in common. Can you spot the pattern? The atom that's attached to the alkene is always part of a pi bond. Do you see that? So for example, the carbonyl, CO double bond, CO double bond, CO double bond. Nitrile, CN triple bond. Nitro, NO double bond. There's always a pi bond connected to the atom that the alkene is connected with. That makes it a good electron withdrawing group always, because there's always that resonance structure possible of pi next to pi that pulls electron density away. So that's a good trick if you forget what an electron withdrawing group is. Ask yourself, is there a pi bond directly attached to my alkene? If so, then it's an electron withdrawing group. The only exception is the trifluoromethyl group. That has no resonance. It's just a pure inductive withdrawer. And as a reminder, you want these groups on the dienophile. In other words, it will speed up the rate of the reaction if you have one of these groups or multiple of these groups on your dienophile. Okay, let's take a look at the electron donating groups. Here are the electron donating groups that you need to know. Number one, we've already seen, it's the ether. Okay, ether is electron donating. How about a reversed ester? We saw that the ester was electron withdrawing, but the reversed ester that's connected to the alkene the other way is actually donating. Amines. And alkyl, just plain boring carbon, is actually a weak donating group. This is a pure pure inductive donor. No resonance. Almost wrote donor like the wrap. I'm getting hungry. You know, the donor. This is like a tasty Mediterranean wrap. Don't write that on the exam. Okay, so notice that the electron donating groups, they all have a pattern as well, in that the site of connection always has lone pairs. And that makes sense because the lone pairs can donate into the diene or dienophile by virtue of lone pair next to pi. So remember that difference to help remind yourself who's your donating group and who's your withdrawing group. Look at the atom that's directly attached to your alkene. If it has a pi bond, it's a withdrawing group. If it has a lone pair, it's a donating group. Let me just kind of highlight what I meant by this reversed ester to compare the difference. So let's just take a look example here. If I connect a reversed ester, it would look like this. Versus the regular ester would look like this. Okay? They're completely different in terms of donating and withdrawing. The reversed ester donates electrons through the lone pair next to pi. So you can see that that's going to put a negative charge on our alkene, showing that it's donating electrons. Versus the regular ester is withdrawing. It does pi next to pi, and electrons get sucked away. Oh, I forgot the plus structure. And that gives a positive charge on the alkene. So depending on where the oxygen of the ester is, how it's attached to the alkene can change whether it's a donating ester or a withdrawing ester. But again, you don't even have to remember that if you just remember the fact that lone pairs at the site of connection are donating and pi bonds at the site of the connection are withdrawing. So let's just draw now an example of an optimized Diels-Alder. Okay. The optimized Diels-Alder would have a electron donating group on our diene. So let's connect to our diene one of these electron donating groups. Let's put on the ether. So we'll put an MEO group on there. Okay, so now that is a good diene. It's got a methoxy group on there, and that's a donating group. Now let's get a dienophile. And on the dienophile, I'll put an electron withdrawing group. Let's put an ester on there. Not the reversed ester, just the regular ester. So there's our dienophile with an electron withdrawing ester group on there. Now that is nice, because we've got here an electron donating group on our diene. And we've got an electron withdrawing group on our dienophile. So this Diels-Alder reaction is going to go blazing fast. And we're going to get the following product. We're going to make this 6-membered ring. Okay, and then remember we still have an MEO group on here. And then down here in the corner we have a ester. So remember, everything that we put into the Diels-Alder reaction is going to come out the other end connected to the 6-membered ring. So if it helps you, you can number the carbons. 1, 2, 3, 4, 5, 6. And so notice we're going to connect 1 to 5. And remember that connected to carbon 2 is our methoxy group, and connected to carbon 6 is our ester group. And so that should all be preserved in the product. So a very common mistake is for students to move the substituents around after the Diels-Alder reaction. Like, for example, they'll put this methoxy group at the 1 position when it's not there. It's on the 2 position, for example. All right, we're almost done. Actually, not much more to say about the Diels-Alder reaction, although we do have to talk a bit about the mechanism and stereochemistry. But before we do that, that'll be the last thing we talk about. I want to show you some common dienes that are used in the Diels-Alder reaction, as well as some common dienophiles. Okay, some common dienes. The simplest diene is butadiene. We already saw this at the very beginning. It has just hydrogens all over it. It's not a very good diene, but it is a common diene. It's not good because it doesn't have donating groups on it. You can make it a little bit better by putting a methyl group on there. Remember, the methyl group is a weak inductive donor, so it is considered a donating group. And you could also have the methyl group up here at the top, no problem. By the way, these dienes are sometimes called monosubstituted because there's one thing hanging off of the diene. We could also have 2 carbons added. This is a very common diene in a Diels-Alder reaction. We've got 2 carbons at the 2 and the 3 position. Or this diene with 2 carbons at the 1 and the 4 position. You could also have rings. Rings are pretty good at Diels-Alder reactions because a lot of times they're locked in the S-cis conformation. So you could have the 5-membered ring with the 2 double bonds. You could have the 6-membered ring with the 2 double bonds. You could have 5-membered ring with oxygen and 2 double bonds. So these are called rings, ring dienes, since they are rings that also have dienes. And those are pretty good at Diels-Alder reactions, like I said, because they're locked in the reactive conformation. And these could all be considered di-substituted, because all of these dienes have 2 things actually attached to the diene component. So like, for example, if you look at the diene here, how many things are actually connected to the diene? You've got 1 thing here and 1 thing here. So you've got a di-substituted diene. How about some common dienophiles? Okay. One of the most common dienophiles is acrolein, which has the following structure. It's an aldehyde attached to an alkene. That acrolein is found in burnt toast, and it's a carcinogen. So never eat burned toast, or at least don't eat too much of it, because it can cause cancer, and because it contains this compound acrolein. The alkene with an ester attached is a common dienophile. It's called acrylate. So common. Also found in burned toast and burned coffee. So sometimes if you go to Starbucks, you'll see a warning there that says, warning, contains acrylates. That's this sort of substance, and that's in the coffee. Also a carcinogen. I mean, pretty much everything's a carcinogen if you have enough of it. You could also have double ester on your dienophile. That's really good. It's got 2 electron withdrawing groups on it. You could also have it with the other stereochemistry. So that's the trans version, but you could also have the cis version where you have the 2 esters on the same side of the alkene. You could have double cyanide, cis or trans. Those are both good dienophiles. You could have a super dienophile. Check out this one. Remember the cyano group or nitrile group is a good electron withdrawing group. You could put 4 nitriles on an alkene, and that is a quadruple activated dienophile. It's got 4 electron withdrawing groups on it. That's the most that you can have. That is an insanely reactive dienophile. You could also have dienophiles as part of rings as well. This is called maleic anhydride. It's got a dienophile right here, this alkene, and it's got 2 withdrawing ester groups on it, so it's a good dienophile. And then finally, we could even have alkynes. I mentioned that alkynes could act as dienophiles, and so you can have an alkyne with esters on it as electron withdrawing groups. And so it's actually the alkyne here in the middle that's acting as the dienophile. So there's a few dienophiles for you. Okay, so really quickly, I want to recap how this mechanism works. We're not going to go too far into detail with the mechanism, just a little bit more talking about the mechanism, and then I'm going to show you about the stereochemistry. The stereochemistry is important, so we do need to consider that. Okay, some notes on the mechanism. The mechanism is concerted. That means the mechanism occurs in a single step. And again, what we saw, the mechanism, it looks like this. Get that ring of electron movement to give us the cyclohexene product. And if you look at the transition state of this reaction, it looks like this. You've got a 6-membered ring. Well, I should actually draw it like this. You've got the diene in the dienophile, and then in the inside you've got this delocalized electron ring that shows the bonds partially forming and breaking. And that's a transition state. So it's a total of 6 electrons delocalized. Okay, so anyway, I'm not going to make you draw the transition state. All I really want you to know is that the transition state is where all the bonds are being made and broken at the same time. It's sort of similar to the SN2 reaction in that sense. Instead of the SN1 reaction where the leaving group leaves and then the nucleophile comes in, it's like the SN2 where everything's making and breaking at the exact same time. That's all I want you to take away from this transition state. Now, let's take a look at the orbitals in this process, because that's pretty interesting. In fact, we could spend a whole class talking about the orbitals in Diels-Alder reactions. But if we draw the orbitals of the Diels-Alder reaction, what we'll see is something interesting. A lot of people think in the Diels-Alder reaction that the diene, here's my diene, it looks kind of like a C, and the dienophile, which looks kind of like a line, come side to side. But that's not actually true. They don't approach each other like this. Instead, they come like an elevator from top to bottom. And the reason for that is the orbitals. So if I draw the p orbitals of the pi bond of our diene, they look kind of like this. It's kind of a perspective view. And then these are the p orbitals of the dienophile. And what ends up happening is that you have some phases on these orbitals. So for the diene, it's shaded on the bottom and then the top. Okay, remember we kind of drew these diagrams in our conjugation chapter where we were talking about the HOMO-LUMO gap. And so this would be the orbitals of the diene on top. And I'm not going to make you draw this. I just want to show you because it's kind of cool. And then the dienophile it's got one node, so one shaded on the top and one shaded on the bottom. And look, you'll notice there's phased overlap from the bottom. Can you see that? So, and also from the top. If the dienophile approach from the top, it would also match up. You've got white with white and black with black. That's phase matching, and that's why the reaction occurs. You've got that nice orbital overlap. So notice that the dienophile can come from top or bottom, but it doesn't approach from the side. It's like an elevator coming. It's an up and down interaction. And overlap p orbitals in phase. Okay, I'm never going to test you on this. The only thing that you need to take away from this little part of the lesson is that because the dienophile can come from the top or the bottom, you can get multiple stereoisomers forming. You can get the enantiomer to form. Just like in the SN1 reaction when the nucleophile could come from the top or the bottom, it's the same picture here. So we're having the dienophile come from the top or the bottom. So let's take a look at an example of how the stereochemistry can matter. Okay. Let's say we took this diene, which would be a pretty good diene in a Diels-Alder reaction. It's got electron donating methyl group at the 3 position. And then let's get a really good dienophile. Dienophile with 2 nitrile groups. That's a dienophile with 2 electron withdrawing groups. That's a really good dienophile. So this is going to be a very fast reaction. At the end of the reaction, we're going to get this, and now there's 2 stereocenters that form. And take a look. The starting material is cis. So we want to end cis. If you start cis, you end cis. And so I'm going to put the 2 CN groups both wedged. Okay. They were on the same side of the dienophile when we started the reaction. They're going to be on the same side of the cyclohexene at the end of the reaction. And what's important here is that we're going to say plus enantiomer, because we're also going to form the product where the 2 CN groups are on the same side but dashed. And that's because the dienophile could either have come from the top or the bottom. That leads to the enantiomer. Let's take a look at another example here. Let me see if I can actually scoot everything up so I can write it right next to it for contrast. Okay, I'm going to squeeze it right underneath here. Let's do the same diene, but now I'm going to do the trans dienophile. Okay. At the end of the reaction, we're going to get the same product. The only difference is now the CN groups are trans to each other. Okay, so the stereochemistry of the dienophile matters. The stereochemistry of the starting dienophile matters, because if you're trans when you start, you're going to end trans. And if you're cis when you start, you're going to end cis. And of course, we're also going to get the enantiomer, so I'll just write plus E. Okay, so that's easy. Okay, no problem at all to determine the stereochemistry of the product looking at the stereochemistry of the dienophile. But what about the stereochemistry of the diene? Does that also matter? Let me show you. So let's say, for example, we had this. And we reacted it with this simple dienophile. What would the product be? Would the product look like this? Or would the product look like this? In other words, these 2 methyl groups, are they going to end up cis to one another in the product? Or are they going to end up trans to one another in the product? That's important. Here's the trick to help you find out. Consider this your diene, and then label the positions at the end of the diene. This is out because it's outside, and this is in because it's inside. This is in, and this is outside. If you react this with an alkene, the outside groups become cis to one another, and the inside groups become cis to one another. So outside, inside. Then down here, outside, inside. So you can see in our example above, both methyl groups were on the outside. So this would be the preferred product, where the two methyl groups are cis to one another, and not this, where they're trans. So this is the correct product, and this does not form. Let's try another example. Okay, I put some methyl and ethyl groups on this alkene, and let's react that with our dienophile. The reaction, by the way, sometimes you'll see it takes heat as a reagent, because the Diels-Alder reaction does typically require heating. So you may sometimes see heat as the sole reagent. And let's go ahead and draw the product. So we know it's going to form a 6-membered ring. And we know that we're going to have a methyl group that's on the outside at the top, which is going to be cis with the ethyl group, which is on the outside at the bottom. And it's going to be trans with the other methyl group, which is on the inside. Okay. Let me show you a Diels-Alder reaction with an alkyne. I mentioned that the Diels-Alder reaction can work with an alkyne as the dienophile. So if we have our diene looking like this, and we have the following alkyne, let's do alkyne with double aldehyde on it. Remember, the alkyne doesn't have stereochemistry. It's totally linear, so we don't have to worry about cis or trans. When we do the Diels-Alder reaction, I'll draw a little triangle to show heat. Now, the Diels-Alder reaction is going to produce a cyclohexadiene. There's going to be 2 alkenes in our 6-membered ring, and that's because if we draw the mechanism, you'll notice the triple bond here on the right, the triple bond on the right gets downgraded to a double bond, and that's why it's a double bond in the product. And we still have our aldehydes there attached. Okay, notice no stereochemistry. It's totally flat because it's still sp2 hybridized. So that is the Diels-Alder with alkyne. Now here's something really fun we'll finish off with. It's something called bridged bicycles. Okay. Let's imagine we used one of the dienes that's in a ring. Okay, so like this one here, plus this dienophile. How can we draw the product of this? Well, we can draw the arrows. Boom, boom, boom. And we know this is just a Diels-Alder reaction like any other. So it's going to form a 6-membered ring. The only difference is, take a look. If I number the carbons here, 1, 2, 3, 4, 5. I'll number the oxygen 5. 6 and 7, let's number it in the product. 1, 2, 3, 4, 6 and 7. Well, 4 and 1 are still connected to 5, aren't they? That bond never broke. So what we need to do is draw the oxygen on the inside, making a bridge. So there's a bridge over the ring between 1 and 4. And notice that on the bridge I made them both wedges, because look, both of these groups are on the inside of the diene, not the outside. So, or they're on the same side, they're both on the inside, so that's why it's cis and not trans. Okay, that's why these are both wedge. And sometimes you can demonstrate these with a side view to kind of see a little bit better. So from the side, it looks like this. You've got this oxygen bridge, and then the 6-membered ring is underneath it. That's the kind of side view of this molecule. But you can draw the top-down view. Don't worry about it. So one thing that's kind of interesting, fun story, is there's this substance called cyclopentadiene, which looks like this. It turns out if you leave it in the shelf for about 4 months, 4 moths, 4 months, it turns into solid gunk. So normally this is a liquid, but if you leave it just on the counter, it will turn into like a solid. What's going on? Well, it turns out it does Diels-Alder reaction with itself. So one cyclopentadiene acts like a diene. The other cyclopentadiene lines up 90 degrees and acts like the dienophile. Boom, boom, boom. So it's two rings doing a Diels-Alder reaction with each other. And let's take a look at the product. So again, it's a Diels-Alder reaction like any other. So it's going to make a 6-membered ring. There's going to be an alkene over there on the left. And then on the right side, we have the cyclopentane is still there. Okay, that was part of the dienophile. And then we also have this little bridge here from the original cyclopentadiene. That's the bridge right here. That's these two carbons right here. So that's a funky looking molecule. And if we draw it from the side, it looks like this. And this is called dicyclopentadiene. Dicyclopentadiene. And that's the solid gunk. So it does Diels-Alder reaction with itself. By the way, I won't make you draw anything like this on the on the exam. I'll show you how to draw them if you want, but they're kind of tricky. They take some practice, so I won't put it on the exam. And I also see I did a typo here. It's dicyclopentadiene. Okay, so that's all you need to know about the Diels-Alder reaction. And just to quickly recap what we learned that the Diels-Alder reaction is a reaction between a diene and a dienophile. So a diene and a dienophile where the only reagent is heat. You don't need anything else. We learned that the reaction works best, or in other words, it goes faster, if you put donating groups on the diene and withdrawing groups on the dienophile. Then we defined what those groups were. The withdrawing groups were carbonyl, nitrile, nitro, and trifluoromethyl. The donating groups were ether, reversed ester, amines, and alkyl. And then finally, we looked at the stereochemical outcomes of the Diels-Alder reaction. We saw that in terms of the dienophile, the starting stereochemistry of the dienophile determined the stereochemistry in the product. For the diene, again, the stereochemistry of the diene also had an impact on the stereochemistry of the product. And so we saw the effects of that in several examples. So now what we have to do is just do a lot of practice, and you'll see that these are all pretty easy once you get over how different all these reactions are from everything else we've learned. Okay, well that's it for now. I'll talk to you guys later. Bye-bye.